Lesson 4, Exponentials and Logarithms. We're using chapter 13 and I'm going to do examples very similar to what you find there and looking at exponentials and modelling. So this is part 4 of the 6-part series we're doing on exponentials and logarithms. So we're going to do most of this through an example, a couple of examples. Firstly, Bonzo Bank charges 30% interest rate per annum, PA, and that's what you get there. And it will at times charge smaller amounts, more often such as 15% for 6 months or 10% for 4 months. So it may choose, Bonzo may say, right, we're going to charge you the interest rate every month or every day or every 6 months. Now, assuming that Fendi borrows £500, silly dog, and how much we're going to find out how much does Fendi owe at the end of 1 year if she doesn't make any repayments and the interest rate charged is, and you've got 5 examples. So we're going to say if it's charged once a year, and how much does she owe after 1 year? If the interest rate is charged biannually twice a year, then how much does she owe after 1 year, etc. So key to this, 2 things are we need to remember that it's all about multipliers, and we must make sure our units are correct. So just a few things we can sometimes slip up on. Here are the answers. So our multiplier is 30% interest, so it's 1.3. That's how it starts off with per year. After 1 year, it's the principal amount, what we call the principal amount, 500 times that 1.30 to give us £650. Now, if it's after every 6 months, every half year, then the interest rate is now 15%, but it's done twice after that 1 year. So again, it's the principal amount times 1.15 to the power of 2 gives us £661.25. If it's charged every month, 12 months in the year, so we divide the interest rate of 30 by 12 to get 2.5% interest rate per month, and this is done over 12 months. So it's £500, the principal amount, times 1.025 to the power of 12, giving us a value of £672.44. If it's done every week, we divide the principal amount, we divide the 30% by 52 to give 0.576, etc. And that, we could divide that by 100, add to 1, so we get 1.005762 to the power of 52. Or we can do it this way on the calculator using our fractions button to the power of 52, and we come out with £674.35. You should start to notice something here, and that's kind of key. What about if it's every day? Well, we do 30% per annum, divide that, so now what is it per day? And this is a formula we can use here. It's a very small fraction, but it's to the power of 365, and that comes at £674.85. This is assuming 365 days. Obviously, if it's 366, will it make much difference to that value? Because what are you spotting here? What are you noticing? What is it tending towards? I decided to graph it. When it's tending towards something, it's always good to use Desmos and graph. And this is what I got. And you can see it's tending towards 675. That's a log graph. You could try and find the name of it all, but it's quite complex and not needed at this stage. Now, let's time to blow your mind. What happened as value tends towards 365 days? We saw the value went towards £674.85. What happens up to 4 years? Well, it's only 3p more. So after 4 years, it's £674.88 that she owes afterwards. So let's now consider what it looks like here. Get rid of the principal amount, and let's just consider this value here. If I got rid of the principal amount, I notice that the multiplying here is 1.350. That's after 1,460 days. What happens after 5,000 days? Well, the same value. It's that same value. Okay, let's blow your mind extra time. Let's consider if Bonzo's bank charged 100% rate. Then what happens? Let's ignore the initial amount and let's consider what the increased value is. Now, I looked at that messy equation there, and because there's factors of 100 everywhere here, I could actually clean that up and it looks like that, much cleaner. So what happens when n becomes large? So let's try it out. I tried it with 3 values. Here are my 3 values. What happens when n was 100? Well, this became 2.705. When n became 1,000, then the value here was 2.717. And when I put 5,000 into this, I came out with 2.718. And there's something special about that number. You might recognize it, you might have seen it somewhere, but it's something very special. Now we're going to look at continuous compound interest. In order to do this, we have a general formula that we use. A is the final amount. P is the principal amount, how much is at the beginning part of it all. E are exponential, bit of a clue there. R is our rate of interest, and T represents the number of, and it can be minutes, days, weeks, years. It could be of anything determined by the question, but also everything then must be put to that unit. Here's an example. Harriet Stanley's fingernails grew at a rate of, and here's the formula. You can see it's an exponential growth. So the L represents the length of the nail, and T represents time in days. So how long were her nails at the start? How long were they after 2 weeks? And what was the rate of growth after 2 days and after 2 weeks? So these questions, what I'm going to do is I'm going to answer them in a minute, but you may want to pause. And now let's go through and see what the answers are. What happens when at the start? Well, T is 0. Anything to the 0 is 1. So her nails were 2 plus 10. And now we haven't assumed it, but let's say these are millimeters. So her nails at the beginning were 12 millimeters long. After 2 weeks, notice we've converted it to days, so 14 days. How long are her nails? Well, 14 goes into there. 0.1 times 14 is our 1.4. So we get the answer of 42.552 millimeters. Now, remember, this is assuming she doesn't bite her nails. So if she didn't bite her nails or clip them, whatever it was, then they would be more than 4 centimeters long. Now let's look at the rate of growth. Now the rate of growth is a rate of change. It's a change. You should remember what that is. That's calculus. So we're looking at differential. So we're looking at how much rate of length is in respect of time. So dl over dt. So we need to differentiate the equation. The constant becomes 0. And don't forget, when we differentiate an exponential, the constant k there drops down. And so we get that here. So it's 10 times the 0.1, which is 1, e to the 0.1t. And that's what we get there. And we simply substitute the values in. Again, the right units. If I put 2 in here, I get 1.2 millimeters a day growth. But after 2 weeks, so substituting 14 in, so 14 times 0.1 is the 1.4. If I put that in, I get 4.1 millimeters growth a day. Now let's look at it slightly differently, going the other way. Here, Tom, the incredible shrinking man, measured 160 centimeters on the day we met. He told us his height can be measured thus. H, his height, equals 160 e to the minus 0.002 t, where t is measured in days. Firstly, you're asked to make a sketch of h against t. Secondly, you're asked then to determine Tom's height after 40 days and after 365 days. And lastly, you're asked to measure the rate of his height loss after the same 40 and 365 days. Again, you can pause it and I'll show you what the answers are in a second. Here's a sketch. Now this is an exponential decay, so we can see it goes downwards. At t is 0, we know that it cuts it at 160 centimeters, but we also know that there's a steadily decline and it's tending towards something. A bit like the previous example where it tended towards something, this is now tending towards something this way. So like the previous example, we simply substitute into the equation our formula, our values for t. Here, when t is 40, we know that the height is 147.70 centimeters. What about when the height is 365 days? We put that in there, and we find that height now is 77.11. So after 1 year, his height has dropped from 160 centimeters to 77.11 centimeters. What's his rate of height loss? Okay, again, rate of change. So it's a calculus, and we have to differentiate the equation. H equals here. Differentiating that, again, it's an exponential, so that constant drops down, and we get now the coefficient of negative 0.32 e to the negative 0.002 t. After 40 days, substituting t now as being 40, we get a rate of change of negative 0.295, which we then say is 3 millimeters a day's loss. We don't say minus, we say it's 3 millimeters a day loss. When we put 365 into this equation, we get the rate of change of negative 0.154. So roughly 1.5 millimeters a day's loss. Hope that's helped. You can now do some questions on exercise 13.3.